So we've talked about Nash equilibria of games of imperfect information. So now let's talk about subgames and subgame perfect equilibrium. So we need to be very careful when we're defining subgames of a game that has information sets. So we're going to define a subgame of game of imperfect information to be any subtree that has the property that if you have some node in an information set, then every other node in the same information set has to be in the subgame. That is to say, you never have uncertainty about which subgame you're in. This is quite a strong restriction. So, for example, if we have, if we're assuming perfect recall, that is to say, no path that hits the same information set twice, then this implies that the node that becomes the root node of the subgame has to be in a singleton information set, because if that node was an information set with any other node, then that node would have to be in the subgame, but it has to be below the root node because every node is below the root node. So this can't happen. As I say, you would have to be able to reach it with some path starting from the root node. So this can't happen. So, for example, yes. So if you have a perfect game of perfect recall, then the root node of every subgame has to be in a singleton information set. So it can very easily happen that we have games that have no subgames other than the game itself, so no proper subgames. So as an example, if we take a normal form game and we translate it to extensive form, we're going to get a game that has no proper subgames. Okay, now we've done this, we can keep the definition of a subgame perfect equilibrium the same. Namely, it's going to be a pure strategy profile that is that restricts to a Nash equilibrium on every subgame. There's a subtlety here where we can still restrict a strategy profile to a subgame exactly because information sets are kind of inherited completely to the subgame. So let's just say all nodes in the information set go to the subgame. That is the thing that makes this make sense. And of course, if we have a game that has no subgames except for itself, what this means is that a subgame perfect equilibrium comes out to be just the same thing as a pure Nash equilibrium. So as a consequence of this, we get, because we already know that there are games of imperfect information that have no pure strategy Nash equilibrium, like for example, translating matching pennies into extensive form, this implies that we can have games of imperfect information that have no subgame perfect equilibrium. So this contrasts with the situation for games of perfect information where we always get at least one subgame perfect equilibrium by backward induction. So we can actually extend the backwards induction algorithm in a way that will compute subgame perfect equilibria for us, but it will necessarily have to occasionally get stuck because there is no subgame perfect equilibrium to be found. So remember how the backward induction algorithm worked. We continuously choose a node whose successors are all leaves, and then we eliminate it and replace it with some leaf. So what we do instead of that is, instead of choosing a node whose successors are all leaves, we choose what's called a minimal subgame, where a minimal subgame is going to be some subgame which itself has no proper subgames. That's the appropriate thing to choose instead of a kind of end node. And what we're going to do is we're going to take that subgame and we're going to find some pure strategy Nash equilibrium of it, and then we're going to replace that subgame with the leaf that we get from playing that pure strategy Nash equilibrium. And so the way we can get stuck is, of course, that we can get a minimal subgame which has no pure strategy Nash equilibrium, and then there's nothing to do, and we just have to give up. And so we repeat this until we get no proper subgames. No, that's not right, because if we get even if we have no proper subgames, we can still solve this for Nash equilibrium. So we actually want to continue until we have only a single leaf, or if we have moves of nature, the thing that we end with is just a single node owned by nature, and then a bunch of leaves coming off it. So we again get the result, the kind of completeness of this algorithm, that the result of this, if it succeeds, is always a subgame perfect equilibrium, and every subgame perfect equilibrium can be reached this way by choosing your Nash equilibria appropriately for the subgames. But yes, we can be in a situation where there is no way that this algorithm can actually end. So let's demonstrate this. So here's the marked entry game. This thing has exactly one minimal subgame. So this whole thing, the game itself, is not minimal because it has this thing as a subgame. This thing is minimal. This has no subgames. So this subtree is not a subgame because it contains this node, which shares an information set with this node, which is not in the subtree, and vice versa. But this thing's a subgame because every information set is completely contained inside the subtree. This thing doesn't count as a subgame because it's just a leaf, it's not a node. So what we need to do is we need to solve this game for pure strategy Nash equilibria. So here I cheated. I just wrote down by cheated, I mean I used a computer, I used Gambit. So I put this into Gambit, and Gambit tells me that this thing has a pure strategy Nash equilibria where both players accommodate. Both players go right. So the leaf that we reach from playing out this pure strategy, this Nash equilibrium, is this one, 3-1. So what we're going to do is we're going to eliminate this entire subtree and replace it with the leaf 3-1. So this we do here. And now this thing is a minimal subgame of itself. So this thing has no proper subgames, but it's still a minimal subgame of itself. So we can solve this for its Nash equilibrium. This is a one-player game, so this is just a long-winded way of saying what we normally do, which is we choose the action that leads to the highest payoff for the player who owns it. In this case, we're owned by player 1, and they could quit and get a payoff of 0, or they could continue and get a payoff of 3, so they're going to choose to continue. And so at the end of this, so now we're left with just this leaf, and so we terminate. And at the end of this, what we've done is we've chosen a strategy profile, namely, so we've chosen a strategy profile for this subgame, which is a choice of action at every node, and note that player 2's strategy is valid. It does the same thing on both nodes in its information set. And then player 1 chooses continue. So the strategic play of this subgame perfect equilibrium is here and here and here, and we get this payoff 3-1.